Welcome to the next session of Embedded Software Testing Unit 3 series. This is the second session in this Unit 3, and we will study about the static testing aspects like static analysis, code review, instructions, tools, etc. And today we will start on the data coupling, data flow analysis. So before that, we will just do a recap of what we have studied in the earlier session. We had a look into the static testing, and we know that it's a component-based testing without execution of the embedded software program. We will do a evaluation of the system without the need of executing the program by analyzing the various aspects of the embedded software system. In context with dynamic testing, the static testing is against execution not needed. So basically, for completion of embedded software testing, we need to have both these type of techniques to be tested as a complemented testing technique for each other completion. So the different types of static testing is on static analysis, review, inspection, and test process. Then we have testing metrics which are used in terms of reporting, tracking, and making sure that the testing is complete in all aspects. In static analysis, we had gone through the type of analysis that we do, identify unreachable code, parameter type of mismatches, possible array bound violations, faults that are found by the compilers. It could be general, info type, warnings, or any errors. So these type of issues which are going to be reported by the compilers are also analyzed statically. And with the help of the code, we will do the program complexity. As the complexity increases, the fault density increases. We know that we should limit the complexities to a certain extent so that the complexity of the program is controlled and within the limit. Also, we had highlighted about the advantages of the static analysis, when it can be done. As soon as the code is done and compiled, it can be used as it is. We have the understanding of the program and the requirements and design, so on par with that, whether it is there or not. So we can do a preliminary sort of a evaluation of the developed code or the program. So that is why static analysis is effective when as soon as the code is done. Better to do it in the beginning than in the end or the after dynamic testing is completed. Also, we have a representation of the control flow, call tree, sequence diagrams, class diagrams, depending on the embedded software system. So that is also used for analyzing the project or the program. So that also will be part of static analysis. Static analysis. So the main aspect is one of the main aspect is control coupling and data coupling. Data coupling, the dependence of the software component on data, not exclusively under the control of that software component. It means the dependency of the component on particular data is not getting controlled by the same component, but getting used or shared between different components. How the data is being coupled between these components is what is being done in the data coupling. And control coupling, the manner or degree by which one software component influences the execution of another software component. So that is what the control coupling is about. Basically, we do an analysis of the various paths of the program in terms of how the control is being done in the entire life of the software program. Embedded software program is being analyzed. That is what we do with the control coupling. So these two are the definitions from the CAST paper. It is from the FAA, Federal Aviation Academy. It is one of the mandatory group which qualifies or certifies the avionics or the airlines or aerospace software products. So examples also we have studied in the other section, and with the help of control coupling, control flow analysis, we can see if there are any unreachable path or unreachable paths partially or completely. If there are any parametric issues so that the flow is not proper, and we can have a visual inspection of the control flow. Also, we do a software complexity. It's called a static matrix, which we study in detail in the later sessions. McCabe software complexity, lines of code, nesting levels, fan out and fan in. Then we had gone through psychometric McCabe complexity with little details like cyclometric complexity calculation is done with the help of edge minus nodes plus 2, and if in case of any disconnected paths are there, it will become a P depending on the number of paths. P is nothing but the path. So complexity basically depending on the edges and the nodes. So these are derived out of its diamonds or the processing blocks within the software program. So if the software complexity is greater than 10 means the complexity is high, and some of the industries they call for rework of the particular product simply because they don't have a complex program because the chances of errors are very high. So basically the complexity, McCabe complexity number specifies the number of independent paths the program has. And we also saw few examples of the cyclometric complexity. It is very important to understand. In the first case we have only one, the complexity is 1 because we have 2 nodes and 1 edge. In the second one we have 4 nodes and 4 edges. So here the complexity is 2. The next one we have the complexity is 2. Why? Because there are 2 paths and they are disconnected with the help of 4 nodes, and there are 2 edges. And in the last one we have 5 nodes and 5 nodes and 4 edges, meaning to say that it will become 1. The complexity is 1. You can see the independent execution path is only 1 from the first node to the last node. Some more examples reported from the tool such as understand C++. Maybe you can go through that. This is from the LDRA testbed. Here you can see the various paths being arrowed with the different nodes and the edges. Here the McCabe is 10. In the next one we have more complex program. You can see there are a lot of nodes have been connected with different edges. The complexity here is 20. In the next one we have complexity as 46, very high. So definitely this will call for a rework because the program can crash or the program may have a lot of errors and bugs which is difficult to fix. So this kind of a McCabe complexity is better to get avoided. So with the help of tools it is easier to analyze such a complexity. So hence the tools are getting used. And static analysis we will study, we will continue today. We know that control coupling we have the flow of the program controlled and the independent execution path or dependent execution path has been analyzed. So in data coupling, basically depending on the objects or the data that is being used entirely in the software program. So data will work better on sequential code. We know that when there is a complex code, so we need to analyze the data in terms of its usage as well as the flow. So ideally we will do a visual inspection of the data flow. Examples, so we will go through the definitions with no intervening views. That means we will just try to understand so what is the definition usage. And attempted use of variable after it is killed. That is especially this is in embedded C++. How the data is being used, how the data is being initialized and updated in the entire program, and likewise attempted use of a variable after it is killed. Similarly, after defined, how the attempted use of the variable is being used in the entire embedded software program. So that also will be analyzed in the data coupling or the data flow analysis. Okay. Coming to the next slide. Static analysis, data coupling, data flow analysis. So there are data which are undefined but referenced variables we have. So we should remove from the code. Unnecessarily we have some data which are either referenced but undefined. So there is no point in having that. Similarly, we have variables defined but not used in the scope. Either should be documented in the code or should be mentioned separately. And variables redefined with no use in between should be documented, if not close to or close it. It means to say that if you don't want to have a redefinition of the variable without any usage, then you should document it. Here documentation is you should comment it if it is going to be used for later stage, or if not used, you can close that variable and delete it. Then the casting. This casting is a very important term. They use it in the embedded software with the different types of variables being interchanging the contents of that. So while doing that, we use a typecast and all that with the help of embedded C. And while doing that, there is a high chance that we lose information in terms of some bits being discarded, and also there is a chance that there is a mismatch between the intended use and the actual use. So if unavoidable, use explicit cast. That means better you explicitly typecast that particular variable. So we have variable temperature assigned to variable redvar. These are log values. Suppose if this is a 16-bit integer and this one is a 32-bit integer, then the best thing would be temp should be assigned with the help of 32-bit typecasting with the red val, so it will be aligned. But we should be careful in such a way that the actual value with the help of 32-bit we will not lose any information. It could be vice versa also. If it is 16-bit that is being assigned with the help of the 32-bit on the right hand side, then the chances are that the data outside the 16-bit we may lose. So we need to be appropriately using it when we are doing the casting. Such errors can be analyzed in static analysis, and there could be a mismatch between the data, what is being used, and what is being assigned. So that also will be brought out while doing the static analysis of the data flow and the data coupling. Global variable analysis, local overrides global. So we know that we use global variables which are used as a parameter shared object between various functions of the procedure, and sometimes the same names are used within the local function, and there is a confusion in terms of usage, and while using that function assumes that the programmer whoever has written assumes that the local variable will be updated, or the global variable will be used or updated within the function, but local gets the priority, or it overrides the global basically. So such anomalies should be removed. The best way to have is avoid the redundant variables. We should have a meaningful variable names, so that it is very clear either it could be a local or it could be a global. So these things we can definitely brought out while doing this static analysis, saying that there is an anomaly between global versus local in terms of its usage and assignment or parameter passing, etc. So all this can be brought out doing the static analysis. Typically, some standards they say that you start the global variables with global variable 1, etc. like that, and local variable start with a variable. So it will be very clear by seeing the variable itself. We know that what type of a variable and where and all it is used, how it is getting used. Similarly, local variable getting identified with a small letter L. So it's a clear segregation of both of them, and there is no anomalies in terms of their usage and the flow. So this is how the data coupling can be analyzed. Okay. The next one being static analysis. Basically, they use it in the unit testing. Why? Because unit testing will be done on the implementation of the code. Basically, that is why it is advisable to use during the unit testing when we do the data flow basically. So while doing the analysis of the code, certain things like project standards we need to establish for the code, like coding standards and the nomenclature of the variables, and the procedure size or the function size or the calls, and the breaks in the cases, like how many cases it can be. Some of the DSPs will not allow more than 4 cases. So in that case, we need to be stringently following the rules of that particular processor or the development environment, such that the program will not have any errors, or it will not go for a crash. Similarly, we know that we should not have go-tos. We know that it is not a good practice to have, because it will have a unintended behavior of the program, and it's very difficult to return from that. So these things are part of the project standards that needs to be established and analyzed against that. So mostly this will be done in the unit testing, and data flow and the control flow can be equally done while doing the unit testing. And other aspect could be remove unused items. That means there are uncertain, unreachable code or the function within the code or the variables, and the declared variables that are not used. So all these parts can be identified either by the inspection or review or with the help of tools. All this can be avoided. So such as unreachable code, declared variables that are not used. So this can be avoided in the implementation. So such things will be brought out while doing the static analysis of the implemented program. And the other important aspect of the static analysis is address design architecture problems. Like there are the flow, control flow and the data flow within the program which is having case statements or the switching statements with the help of pointers or the addresses. That will be difficult to find out while doing the execution. So better to do a thorough inspection or the visual inspection of the control flow. So we are clear about the architecture, how the program is designed, and the various states. This is definitely useful in events, states, or state machines, etc. So in this case, better to have a understanding of the entire program. Then with the help of visual inspection, apply the standards or the architectural rules or the architecture that we have understood in the program, and with the help of control flow graph, we will analyze the design. We will analyze the entire program. Similarly, we have anomalies in the procedures. The procedures are defined, referenced, and not used. Such procedures we should avoid, and the usage of the procedure in terms of parametric values also need to be analyzed while doing the static analysis. That is also an important aspect. Okay, so coming to the next one, we know that control coupling, control and data coupling are analyzed while doing the integration testing also. It is not just enough to have control coupling and data coupling during the unit testing. It is also important to have the control and static data coupling during the integration testing. Why it is important during integration testing is, while doing the integration testing, we will address the different modules, and we know that we are going to integrate various models, and the modules are with respect to software, that means application level, and it could be software to hardware, such as device drivers with the application, system versus application. It could be such sort of a bottom up or the top down approach integration testing. While doing that, it is better to analyze the integrity details of the modules, so that the control and data coupling can be analyzed. Okay, so that is the highlight of that control flow and data flow while doing the integration testing. The next one is being the software integration testing reveals the control and data flow of the program. You know that basically the software integration, as I said, application level or the program level within the modules of the entire program will definitely bring out the control flow of the program, and equally the data and the objects or the variables that are flowed on within the program. So that's how the static analysis can be done in the entire embedded software program. So that is how we will do the control coupling and data coupling in static analysis. So now we will come to the tools part. So what are the tools that are used and how they are being used and in what way it is useful for static analysis. Okay, static analysis tools. A static analysis tool is like an automatic reviewer for your code. That means whatever the human being does, the tool will take care of that basically on the intended embedded software program. So it basically analyzes the code or reads through the source code, of course without execution, and looks for cases where it will behave in an undesirable manner. For example, dereferencing a null pointer, dividing a number by a variable by 0, or overflow of a memory buffer. You know that embedded software program should definitely have a upper bound and lower bound of the memory, and If any variables or procedure is exceeding that, so it will identify those anomalies. So the static analysis tool will work like a automatic reviewer of the code. Static analysis tools do not depend on sample input. Definitely no input, dynamic input or input actual input is required. They can infer the software's behavior based on just the source code, because source code will have definition and the flow of the variables that are intended to be used within the procedure of the function. So with the help of that, so what the tool does is it will try to feed various values, and it will try to analyze the flow of the particular parameters based on its definition and declaration. So that is what the meaning of this second bullet. They can infer the software's behavior based on just the source code. So when a bug is found, the tool reports its location to the reportee or the software engineer, whoever is running the tool, along with the information needed to diagnose the problem. That means it will just point out the problem where the issue is there in terms of the static analysis aspects of the what we have seen earlier, like control flow, data flow issues, which is automated, which is done in the tool, and it will report the location. Basically, it will identify which location has what issue. So this is very important. Why? Because there are stringent rule checker that are being used, and that needs to identify the various anomalies within the implemented program, especially the rules like MISRA C. It's a motor industry standard regulatory rules. So MISRA standards, suppose 2004 has about 120 plus rules are there. Those are rules which are stringent to be followed to be implemented in the program. Also there are mandatory rules and guidelines that also will be understood by the tool. Where the violation is there, violation of the rules and the intended usage of the program and the data, it will report as a error. So since they do not sorry, since they do not depend on sample input, static analysis tools can investigate program behavior in corner cases that are not anticipated by testers and human inspectors. Some of them, such as very small sort of a like pragma, or if it is a macro usage, which is very difficult to analyze or inspect visually. So those things are definitely can be caught out with the help of the static analysis tools, because for that the programmer dependency or the sample input is not required. By simply inferring the program flow or the data flow of the embedded software, the tool will identify such issues which are hiding from the human while doing the inspection. Okay. While no tool can find all bugs, of course, modern static analysis tools generate valuable results with minimal false positives. That means it will definitely aid the tester or the testing team in terms of where could be the problem areas, where are the issues the likely that is going to happen while the program is going to go for a field or program is getting executed. So even for projects with millions of lines of code, definitely the tools will give some sort of a hint or issues, or it can report directly. But wherever there is a problem which it cannot report directly, or if there are errors or issues, so because of one issue it could result in a runtime error. Suppose it identifies a variable as a variable improperly defined. This is an issue. This at least will give a issue. Suppose it's a issue n. This issue n is definitely a clue for the program that can have a bug while executing on the field, or when there is a dynamic usage of the program. It could be any issues like memory, performance, speed, timing, etc. Anything it could be. So at least if it's not in entirety, it may support, but what it can do is it can aid or help the tester in terms of results that can have a some sort of a positiveness in terms of errors or issues that can be fixed to have a major crackdown in the later stages of the program. So that is how it can be used. The tools can be used. Okay, so what are the tools that are available in the market or that are most likely to be used in the embedded software industry? Of course, there are hundreds of tools. Each one have been used, or each ones are being evolved based on their usage and the feedback from the embedded industry. So there are certain few examples which I try to put here, which can be used directly or indirectly, partially, fully, depending on the type of embedded software systems. It could be telecom, could be a railway signaling systems, it could be a automotive or aerospace, etc. One such tool is understand for C++ or ADA from Sky Tools. So basically, this is a good static analysis tool which will identify analysis static analysis aspects like Maccabee complexity, lines of code. It will report the dead code, dead objects, initialization, variable improper usage, then the call tree. You know all this by now. So as a static analysis aspect, all this can be done with the help of understands for C++. It has got a lot of features. I will try to go through a snapshot of the understand for C++ as a practical understanding of the tool in the next slide probably. Similarly, we have a tool like Polyspace. It has its own advantages and disadvantages. They use it in the automotive industry. Similarly, we have Coverity for inspection, reviews, and static analysis. We have a QA checker, QAC, Cantata. Then we have LDRA testbed. So some of these tools like LDRA or RTRT, they can also be used for unit testing where it does the instrumentation. You know that during white box testing we need to do the instrumentation of the code with the test hub and the test drivers. So meanwhile, the same tool can be used for that. This also can help in terms of static analysis, code inspection, reviews, etc. Of course, as I said, the MISRA tools for guidelines and rule checker. We have the IDEs such as Code Compose Studio, Multi, etc. They have an inbuilt feature, so which can be triggered and used on develop the code, so which will report a error or the violation of the MISRA rule, saying that such and such rules have been violated, and that the violations can be reported as a static analysis output. That is how these tools can be used. Similarly, we have Logiscope, rule checker. This is from Perilogic. This is also one of the important tools. Across the industry they use it, and we have the PCLint. So that is also one of the static analysis tool. PCLint is more on is the olden days tool, basically Linux based systems they had used, and for C program, C++ program, is inbuilt along with the compiler or the compiler series programs. This is available. This is an open source static analysis tool. This can be used for static analysis. So these are some of the static analysis tools. So we'll try to understand a snapshot of static analysis testing tool. Here it is understand for C++. I think I will try to create a sample project and explain the flow of understand for C++ how it can be used in one of the practical session in the later part of the course, probably in the end of the embedded software testing course. This is a sample report. You can see this tool has a lot of features such as we can build the program, build the project with the help of embedded C. You can see the source code here, like int main is there. There is a blue letter which it understands from C perspective that the declarations and definitions as part of the implied C source it will highlight, and the variable name it has highlighted at that letter here. So the definitions can be easily understood by the user in terms of analyzing the code and understanding the source code. And here you can see a invocation of a sample program which I have wrote. There is a main, there is a delay which is called by main, and delay is calling the another program called nothing. So this is a call tree. Similarly, we can have a complexity in terms of call tree. Maybe one more slide I have to show you at what deep level we can use the understand for C++ tool. And another window we can have another type of report which shows the other side, like the nothing is called by whom. It can be called by multiple people here, but here in this case only it's a one flow or the one sided one direct call is from main, relay and nothing. So on the left hand side you can see the snapshot of how the particular function or the group of program it can highlight. Here it is defined in main.c. It will list out the global as functions. How many functions are there? There are 3 functions: delay, main, and nothing. And it will report for this particular main.c a matrix in terms of what is the count line. So what is the count line code? You know that executable lines of code 75 is there, and there are 49 lines having comments, and there are inactive. There are 0. That means if there are inactive lines, it will report as so many numbers. So likewise we can have the report. I will try to show you in one of the sessions how we can generate the report with the help of this tool, and you can also download this tool for free or not for commercial use from www.skytools.com. They'll give a 15 days evaluation version where you can create a sample project, sample embedded C or C++ project and analyze the same. Maybe the download part of that you can take care, and maybe I can provide some examples so that we can go through them and try to understand the tool. So this is the snapshot of the understand for C++ static testing tool. So there is one more tool we will go through. This is check marks. Check that's from checkmarks.com. You can see the reference here. This also have a various analysis output in terms of a vulnerable code line. So what is having issue here? It will highlight, and it will list out the project files. What are the files? What are the header files? Here I think it is taking an example, a snapshot of. I think it is a database program. Right hand side, you can see the flow of different programs. It is called attack vector, how it is being ordered. Similarly, results, it will show in red if there is a found errors or issues, and there is a optimal mitigation point. That means how different programs have been controlled and mitigated with this control flow. Likewise, we can use the static analysis for generating the static analysis report with the help of this checkmarks tool. In the next, as I said in my earlier slide, understand for C++. Here you can see a simple program having only 3 programs or the functions which are being invoked. In the next one, you can see the complexity. It is not the flow or control flow complexity, it is the call tree basically. You know, it is, you may not be able to see completely. Maybe when I explain the tool, you can understand the call tree in detail. Here you can see the main function calling it's ADA program. There are about 6 to 7 main next level function. We can call it as a level 1. Then each one of this program or the function will call the level 2 individual functions. There are, each one can have 4 5. Likewise, this is a level 2 at the next after the first invocation is done. Similarly, we have a level 3, we have a level 4, we have a level 5, etc. So, and it also can report in terms of no issues with a green color and issues with of course we have a level 6. So this, the complexity here we can presumably say that as to level 6. Of course it depends on each function and its internal details, and it will highlight with different colors different aspects of the control flow. So this is one of the good example of understand for C++ call tree. With the help of this, the user or tester can analyze how each program or the function have been architected, how each function or the functionality or the individual procedures have been used or the called within the entire embedded systems. So this is very important aspect for static analysis. Okay, the next important aspect for the static analysis is WSET. It's also called as worst case execution time analysis. So we know that timing is very important in embedded systems, especially hard real-time embedded systems. So we need to have a timing aspects clearly analyzed in the program so that we know that what it is going to take. The worst case for a program, it could be any functionality, it could be entire program, or it could be a device driver, whatever it is. So all these have to be analyzed for its time or the timing that particular piece of software it takes. It takes from 2 aspects, best as well as worst. So both have to be analyzed. So very important aspect in embedded software testing. This needs to be analyzed statically. So worst case execution time analysis provides the worst possible execution time of the code before using it in the system. Before actually we use the system on the field or for dynamic testing. The WSET or the worst case execution time analysis of a piece of code depends on both on the program flow, like we have for loops, iterations, then we have decisions such as if else statements, then it depends on the various function calls that are within the program. And of course the architectural factors like cache and pipelines. Of course embedded industry they use cache memory. uh, you know that embedded software will have a cache which is a temporary storage which is being used very frequently, and these factors can be understood while doing the WSET or the execution worst case execution time analysis. And pipelines is nothing but an important processor aspects such as fetch, load, store and execute. So these are some of the stages that core processor or the processor does for executing. So definitely few instruction cycle are involved. Those need to be analyzed in terms of how many instructions it requires, a line of code or a group of lines of code or the entire program or the piece of function. So very important to have a worst case timing analysis in the embedded software testing. So we know that how much it is going to take for worst case execution of that particular software. With the help of the timing analysis we do that, and we will report as a failure if it is going beyond intended timing, and it needs to be fixed by the development team in terms of optimizing the time or reworking on the code, whatever it is. Okay, so the WSET analysis was used to verify real-time requirements, to optimize programs, to compare algorithms and to evaluate hardware. Definitely we need to have a comparison of the various models so that we know how much each model is going to take, so that entirely we know that what is more complex, what is going to take more time, etc. And also we will know and analyze the programs which require optimization, and so and so hardware is behaving this way, it is taking more time. Suppose we have some 3-4 drivers, I would say device drivers, each one takes its own time, like one takes 2 milliseconds, other one takes 5 milliseconds, other one takes 10 microseconds, etc. So we know that overall that particular program, if that is using 3 device drivers, we will know how much it's going to take. So this 2 millisecond could be one read operation or write operation or access, whatever it is. So all this can be evaluated with the help of the timing of that particular program. So this also is a measurement of the time. One of the measurement is timing analysis. Tools used for emulators, time accurate emulators for the program. Emulators will support in terms of the call sequence and the total time of the calls, the stack usage in terms of how much time it has taken, or the call tree, or the sequence tree, etc. So all this can be done with the help of emulators as well as simulators. Then we have logic analyzers which can be hooked into the embedded software, and with the help of logic analyzers timing analysis can be done. And we use oscilloscopes to measure the various timing aspects. We know that oscilloscope will help in doing the plotting. So we have something like this, and we can measure time like this, or any waves in the oscilloscope where we have the time on the horizontal axis and we have the value on the vertical axis, so that we know what is the value across the time it is going to take, and we do the analysis with the help of oscilloscope to probe any signals or the variables. Of course, we have the timer readings of the particular embedded procedure or the variable or the signals. And of course, we have inserted programs specifically for measuring this into the software, and we have the profiling. It's wrongly spelled here. It is nothing but the software profiling. Profiling is a very important aspect in the embedded software systems. With the help of profiling, we will do the analysis of the timing that procedure or the intended program is going to take. Okay, so that is about worst case execution analysis. You can see a example is from one of the web reference that I have used. So here both aspects have been put in this diagram, which has B set and W set. So B set is best case analysis, best case execution time, and W set, you know that it's a worst case execution. So in between, in the middle, you can see that there is a possible execution time, and beyond that there is a one safe zone called best case execution estimates, best case execution analysis. So across the horizontal line, you can see the time, and the program can take from best to worst. So we will do an analysis. We will say this is the tighter one, and we have a border actually where we define the best and the worst. So within this, mostly it is going to execute optimally. If it is less than B set, it is called as a safe B set and estimates or analysis. If it is beyond that zone of this execution time, you can see in the middle, it is called as a worst case estimate. So like this, we do an analysis of the best case execution, and the relationship will draw. So the goal of W set analysis is to generate a safe and tight estimate of the worst case execution time of the program fragment or the program. So a related problem is that of finding the best case execution time of a program. You can see in the program example here, figure, how the different timing analysis have been put together. So this can depict the average execution time, the best execution time, and the tightness, safe estimates. Likewise, we can have. So analytically, it may be difficult to arrive at average execution time because there are lot of statistical profiling of the input data, real-time data, all are required. So it may be very difficult, but definitely we should be able to analyze the worst case. And with the intuition and the analysis of various worst case execution, we will know what is the possible execution time and the best execution time. So for doing that worst case estimate or the worst case execution analysis, so the important steps that we need to take care is the program flow. I will start here. Then we need to have low level flow or analysis, because individual low level analysis will matter in terms of high level program flow collectively. And of course, we have a calculation of all this flow. These three are very important steps in terms of worst case execution. timing analysis. So this is how the worst case execution timing analysis is done. There are, as I said, logic analyzers, oscilloscope, emulators, simulators. Any of the tools can be used for doing the worst case execution analysis. You can see another snapshot of WSET. This is from bounty.com. So there is a what they do is they'll define a boundedness of the program, and surrounding that they will define the various aspects like source code being used from the compiler and linker, which will be applied within the bounty, and that compiler linker can use libraries or kernels, and user assertions in terms of for loops, values, call counts. All this will be analyzed in the bounty analysis, and the analysis is done with the help of decoding the instructions and the control flow, subprogram calls, loop bounds, worst case path. All this will be done with the help of bounty analysis. The inputs are analyzed, and as a result we have a flow graph. As a result we have a call graph. As a result of this bounty analysis, we have worst case bounds in terms of the cycles, the various cycles that each program fragment or the programs will take. Like main will have a cycles of 9352 cycles. There is a program foo which will take 121 cycles, and the count is 105. Solve is 9207. Count is 303. Once is 721. Like this, each program fragment will list out how many cycles, and with the help of that we will do a static analysis of the timing or the timing analysis. The next one is a static analysis in terms of stack analysis. It's also very important aspect. And the next type of static analysis is stack analysis. You know what is a stack? Stack memory has to be allocated statically by the programmer. That means the implementation code should have a stack memory, definitely, because we use interrupts or preemption of the various small functions by bigger functions, or preemption of bigger procedure by smaller functions. Definitely the program state and the variable states all have to be saved and should be recalled. So that is the use of a stack. Definitely embedded systems will have a stack memory, and stack memory has to be allocated how much it is going to take each embedded software fragment or the entire program. Underestimating the stack usage can lead to a serious runtime errors. So we need to have a definitely a safe bound of the stack memory, and allocation is very important, and we should make sure that the implementation of the embedded systems will not go beyond the stack memory. So that is why there will be a hard requirement saying that at least 50% or let's say 75% stack memory should have a reserve. That means in worst case it may exceed, so that on the safer side better we should reserve 75% of the stack, so that if the program spills beyond 25%, still it's safe, because the embedded systems will not crash because there is no stack issue or stack error. Okay. So underestimating stack usage can lead to serious runtime issues. Program behavior can be unpredictable, when there is a stack issue, and which is very difficult to find. Similarly, overestimating a stack usage also we cannot have. We cannot have a 200% or 300% of stack usage buffer or allocation, because we are wasting the memory. Stack analysis calculates the stack usage of embedded application. We know that the analysis results are valid for all inputs and each task execution. Stack analysis can directly analyzed on binary executable exactly as they are executed in the final system. So stack will be same. And stack analysis not only reduces the development effort, but also helps prevent runtime errors due to stack overflow. So it's a very important aspect is that any time of the embedded software system or the program, we should make sure that there is no stack overflow during the runtime. So this also will be analyzed during the stack analysis of the embedded software system in the static analysis. The analysis can also done on the map files generated during the build process. So we know that program will be compiled, linked, and as a result we have a executable with map file. Basically, map file will have the complete picture of the program which is going to be executed on the processor. So the picture will clearly tell the pointers on the memory, like it will list out basically the stack segment, memory, program text, and the data. So this needs to be analyzed, and definitely this will have a stack memory usage and the upper boundary how much it can have. So that needs to be analyzed, and we know with the help of map file what is the stack. So maybe as a practical example, I will try to go through a sample memory file. The memory file will have name with a dot map. So this needs to be analyzed statically. So with the help of that, we will know the memory aspects and the stack aspects of the embedded software program. So with this, we will conclude today's session. We will continue the next session on the static analysis with the stack overflow and what are the guidelines that needs to be taken care for stack analysis in the next session.